All right, let's get started for today. Apologies for the delay. A couple of announcements. Actually, my screen isn't mostly not working, but this is working. So homework 5, reinforcement learning, is due on Monday. Project 3 is also on MDPs and reinforcement learning. It's due next week, Friday. The contest associated with Project 3 will be due after the midterm, Thursday after the midterm. Then today we'll announce right after the break the Project 2 contest results. And we have a lot to say about the midterm, I hope. Here we go. First things first, midterm will be on Monday, March 10th, 6:30 till 9:30. There are 3 rooms. Your last name determines which room you're assigned to. So this is also online, but that tells you where to go. There's a preparation page, which is a lot of information for you. It tells you what topics are covered. It gives you a link to a list of past exams that have solutions with them. There are special midterm 1 office hours, about 12 extra office hours. Take advantage of that if you have any questions. There's a practice midterm. The way that works is you download a practice midterm in some way. You work on it on your own for 3 hours. And after that, you can work on it more if you want, but a minimum of 3 hours, or you ace it and are done before the 3 hours are over, one or the other. Then you scan it and submit it just like you do with homework, or maybe you did it electronically. You submit a PDF. But so you get 1 point of extra credit on the midterm for completing this, where completing means either acing it or having spent at least 3 hours thinking about that particular midterm on your own. So we won't actually grade it. This is an honor code kind of thing. You sign off on the first page whether you think you aced it. That's a tricky thing to sign off on, but it's always cool if somebody does that. And the other thing you can choose, which gives you equal amount of points, is that you spend your 3 hours on it. It's optional, but we recommend it. And the main reason we highly recommend it is because exams are always different than homework. It's different conditions, so it's good to simulate exam conditions ahead of time, see where you are at. So this will be due on the Saturday before the midterm, meaning that on Saturday night after you submitted this, and you feel like, wow, I did poorly, you still have entire Sunday, entire Monday to prepare for the midterm, almost entire Monday. All right, any questions about logistics? Okay, so what's our status in CS 188? So far, we've looked at search and planning. It's really important. It's about decision making, but there's a whole other story there that we're going to look at now, which is about reasoning about uncertainty. And the way we're going to do this is with probabilistic reasoning. What are some applications? So the reason I want to bring forward some applications right now, even though we're not going to cover them today, is because it's a little bit of a drier stretch of material right now. This lecture is probably the least exciting lecture of all lectures we do. At least we have the mini contest results in the middle of it, but I want to tell you why you should care. A very high level reason why you should care is, if you think back to the first lecture, we were talking about the history of AI, and AI kind of hit a dry spell and only kind of got reinvigorated in the 90s, and a lot of why it got reinvigorated and why things started working is because people start using probabilistic reasoning. So rather than assuming you can reason about everything in the deterministic way, allow for things to be uncertain, and probability is the way to do that. Unfortunately, it requires a little more math background, a little more math buildup before we are there where we can really start doing things. There's a stretch here where we have to build up to it, but it was necessary in general to make progress again at that time. What are some applications we'll be building up to? Diagnosis. Let's say you are a physician and you are measuring all kinds of symptoms on a patient. Then what we'll be able to do is, from those measurements, infer a posterior distribution over the possible diseases causing those symptoms. This could be for diseases of a person, this could be a printer that's broken, an any kind of system that you might want to repair. Speech recognition. There's some signal coming in when you listen to somebody. That signal is noisy. It's not always the same. Even the same person might not pronounce a given word the same way every time they pronounce it. So there's some uncertainty there. How do you manage that? How do you go from that signal to the word that was being pronounced or the entire sentence that was being pronounced? Again, probabilistic reasoning will allow us to do that. Tracking objects. Let's say you were sending the Apollo to the moon, and you want to track where it's going, and you might want to adjust kind of the controls and say a little more this way, a little more, a little extra boost from that part of the rocket and so forth to steer it. You need to know where it is. But actually you don't have ground truth. All you get is some measurements, and you hope that you can combine those measurements in the right way to get an estimate of the position and orientation of your rocket. Robot mapping. So let's say you want to map out a building, right? One thing you can do is you can show up with your own measurement devices and try to build a map. Another thing to do is you can actually send in a robot. The robot has either cameras or lasers on it to make measurements, and you just steer that robot through the building, and you can come back out with a detailed 3D map of that building with current techniques, and they all heavily rely on probabilistic reasoning. Genetics, let's say you meet somebody you are considering mating with, and maybe you meet their parents and their brothers and sisters and so forth. You can run probabilistic inference about the quality of their gene pool, and then see how that relates to your gene pool and if you think that's a good match. Let's leave it at that abstraction. Now, another one is error correcting codes. We take it for granted when we get, let's say want to download a page from the internet, we get what we want. But underneath there are electrical signals. And those signals at the analog level are noisy. And a high level might be a 1, a low level might be a 0. But when you transition between 1s and 0s, there's a slope there. And so if you want to send data fast, then these can be sequenced very quickly after each other. And so there could be something noisy happening there where what should be a 1 is coming with a pretty low level every now and then. And so what people do is they have invented this thing called error correcting codes. The simplest version of this is instead of sending a 1 once, you send it 3 times. And then as you decode, you check. And you get these 3 bits, and you just do a majority vote. Whatever is the most frequent bit. If you see 2 1s and a 0, well, they probably sent you a 1. In fact, they probably sent you 3 1s to encode that 1. And so that's error correcting codes. There are much more advanced error correcting codes that don't have to triple the amount of data you send. And we'll look at how that might work again using probabilistic reasoning. In part 2, we'll assume that the models are given to us. We'll have these probabilistic models and we'll see how to reason with them. Then in part 3, we'll start looking about how to learn these models and other related models from data. All right, so that's the motivation, but now we have to deal with some math for a little while to build up to all of this. So today's lecture, in some sense, is going to cover everything we're going to see about probability, and in some sense, almost nothing of what we're going to cover. And here's the subtle distinction. Today we're going to see all the concepts about probability that we need, but we'll also realize that if we want to reason about large sets of random variables, big distributions, what we're covering today is impractical. And in the next lectures, we're then going to look at how to make some of these computations that we need to do faster by exploiting some new techniques. But at the mathematical, at the abstract level, what we're going to look at in all of the next lectures is already covered today. We're going to look at random variables, joint and marginal distributions, conditional distributions, the product rule, the chain rule, Bayes rule, inference, and independence. Independence we probably won't get to today, might be for next time. But those are the main concepts we'll cover for the next 6 or 7 lectures. But today we'll see them all in kind of the standard context. Many of you hopefully have seen what we see today before, and it's a refresher. My recommendation is that everything you see on these slides, if there's anything out there that you look at it and you're not 100% sure from just instantaneously sure what it means, keep reviewing these slides so you're ready for the next lectures, because we'll assume that you understand this very, very well. A bit like once we were doing reinforcement learning, if you didn't know what T stood for, you didn't know what R stood for, there was just no way you could understand the equations on the slides. All right, so let's look at a demo that we can look at already. Ghostbusters. So the idea here is that there is a grid. In this grid, somewhere there is a ghost who's hiding. We don't know where the ghost is, but we know there is exactly one. We can make measurements. If we happen to measure on top of the ghost, we don't know that we measured on top of the ghost. All we get is a color back. We get red, orange, yellow, or green back. These four colors, how they show up depends probabilistically on how close we are to the ghost. If we're on top of the ghost, usually we'll get red, but we could get green. It's not, we don't know ahead of time. It's a noisy sensor. If we're further away from the ghost, the probability of red goes down, probability of orange goes up, yet further away yellow will be the highest probability, and then yet further away green will be the highest probability. So let's see if we can find this ghost, and at some point we get one shot at trying to bust it. So we'll just be kind of sensing, and then at some point we say we think we found the ghost and hit the bust action. If we hit it on the correct square where the ghost is, we win, get a lot of points of high utility. If we bust at the wrong square, we lose. So maybe we start out here, green, not very close probably. Red, likely better, but again, we don't know that for sure, so we might want to measure around it. See what's going on here. A lot of green around it, so maybe that red was just a noisy measurement and the ghost isn't really all that close to over there. This looks more promising, where we often get a warmer colored measurement. So at this point we might say, well, yeah, this looks pretty good. It's noisy, but this is likely where the ghost is. We don't want to waste any more time. Let's take our chances and measure. But keep in mind that we just as well saw red over here. That just happened to be a very noisy measurement. Most likely, who knows? We don't know. There's a small chance the ghost is somewhere completely different or where we measured green. But let's try and see what happens. So let's take a bust action. Ghost remaining 0. We got him. All right. So this actually worked out better than it usually works out with a beautiful red square somewhere else where the ghost actually is not. This is what we're after in this lecture, is dealing with these noisy measurements in a better way than just kind of intuitively looking at this and saying, well, maybe it's here, maybe it's there, let's give it a shot. So towards the end of the lecture, we'll see in this demo some computation happening that will show us where we think the ghost is going to be. Yes?
Why was the red square right next to the green square, surrounded by the orange?
Okay, the reason this happens is because the sensors are noisy, and let's say the distance to the ghost is 3 squares. There's still a 5% chance of measuring red. It's an unlucky measurement in some sense because it's not the most representative measurement you could get if you're 3 squares away, but it can happen. If you are 3 squares away, orange has a probability of 15%, yellow 50%, and green 30%. So each of the distances, 1, 2, 3, or even 0, and so forth, have a conditional distribution that looks like this. Not the same, of course. It varies with distance associated with it. The further away, the more weight on green. The closer to the ghost, the more weight goes onto red. But never 100% certain about what the measurement is going to be for a given distance. Yes?
And in these cases, we don't know the noise, right? Like, we wouldn't actually know what this table is, or we do?
In this middle 1/3, we assume we know the model. And we work with the model. In the last 1/3, we'll see how we can learn the model as we go along. All right, so when we deal with uncertainty, usually we can split the random variables into 2 groups. One group is the group of random variables that we get to observe. We get to measure them. And usually then what we want to do is somehow infer something about the variables we don't get to measure, the hidden variables, the unobserved variables, and do that in some structured way. And the way that is structured is using a model, a probabilistic model that tells us how measurements relate in a noisy way to these hidden variables that we don't get to observe. All right, so random variables. A bit like what we had with CSPs, right? You have these variables that have domains and so forth, and for example, we could have a random variable in this case for whether it's raining or not. We could have a random variable for whether it's hot or cold, how long it will take to drive to work, or the location of a ghost. Our notation is such that random variables are capitalized, all right? Then each of these random variables has a domain. The entries in the domain we denote with lowercase. So, for example, for raining could be true or false. Then often we also write this as follows. So this notation here is something new that we will use a lot. That the domain of this binary random variable that we think of as being true or false is denoted by plus r minus r. The beauty of this is that by looking at this, I'm not just saying true, false, I'm also already indicating which variable I'm talking about. Plus r is not only shorter than true, it also gives us more information. It tells us that it's the random variable capital R that is taking on the value plus r. So it gives us a better or a shorter notation than we usually would have if we were more explicit with true and false. Temperature, hot or cold. Driving time could be continuous. Interval, the domain could be an interval. We're not going to deal with that. We're going to deal with discrete random variables, but similar ideas apply to continuous random variables. Location, what's happening here is that the random variable takes on a pair of values. So there's an x coordinate and a y coordinate, and together they form that random variable. Then we'll go into, yes?
So you had TFN, you said it's hot or cold. So a lot of variables we had there had discrete values where it could be just hot or cold, true or false. But if you have, for instance, T, which you have a probabilistic range or function, can you give a set of probabilities?
So if you have a continuous domain and you need to assign a continuum of probabilities, what you typically would do is we would use a probability density function. It's not going to be important for what we're looking at. We're going to assume discrete domains. But a lot of the concepts we look at, conceptually, they will go through just as well for continuous random variables. Just the math of it is a little more intricate. You deal with integrals rather than summations, which makes the math a little more involved, but the ideas are actually quite similar. And so if you know the math behind continuous variables, you'll be able to generalize what we look at for discrete variables to variables with continuous domains just fine. But we're not going to ask you about that. So each random variable will have an associated distribution. For example, here the distribution for temperature, hot or cold. You can think of it as a table, right? Where the first column is indexing over the values in the domain, and the second column is then showing the probability of each of these values to be the one that happens. For the weather, similar thing here. We have 4 possible values here in the domain, and each of them has an associated probability. By the way, this is usually a bad idea to assign anything a probability of 0, because then there's no point in having it in your domain, but if you think it's possible to have a meteor shower, probably you still want to assign it something like maybe 0.0000001 probability, and then it's sitting there, and if then something funny comes up, it might be explained by that initially low probability, but now the measurements might be very compatible with it. All right, so unobserved random variables have their distributions. What are the constraints on these tables, right? Hold on. Apologies here, our screen is not collaborating, making it hard to see what's going on. Okay. Okay, from this table, you can read off, for example, the probability of the weather being equal to rain, just by looking at that row, reading out the corresponding probability. What needs to be true about these tables is that every entry needs to be bigger than or equal to 0, and the sum of the entries needs to be equal to 1. Otherwise, it's not a probability distribution. That's just a definition. All right, in terms of shorthand notation, this is the longer notation. It's very explicit, probability of temperature being equal to hot. If your domains of your variables, you have a set of things you're talking about in your problem setting, if the domains of your variables are such that t is the only variable that has the value hot in its domain, then you can shorthand this as follows. Because now when you see p of hot, you know the only random variable that has hot in its domain is t, and so you know that's shorthand for the thing on the right. Of course, if all your domains are just 0 and 1 values, if you just write p0 and there's a lot of variables in play, you have no idea what that's talking about. All right. So the thing we'll be interested in is joint distributions. The reason we care about joint distributions is because we want to infer things about variables we haven't observed based on observations we made of these observed variables. Okay, so joint distribution is a distribution that involves more than one random variable. For example, here, joint distribution for temperature and weather. We now have a column for each of the random variables, and then the probability here is the probability of the joint instantiation. For example, 0.4 is the probability for hot and sun to both be happening. Again, a joint distribution is to satisfy the property that each entry is positive and that all entries together, if you sum these together, should give you 1. It's a definition. It's not something you can infer. It's not anything you derive in any way. It's just what it has to be. The first question we can ask ourselves, let's say we have a distribution over n variables and domain size is d. How large will that table be? Over there. So it involves n and d. One suggestion was nd. Any other suggestions? I hear a d to the n. Of course here, d, and in this example, d equals 2 and n equals 2, so d to the n and d times n is the same, so the example doesn't really let us distinguish between the two. It's d to the n. The reason it's d to the n is because you need an entry for each possible combination of the values these random variables can take on. So the first variable can take on d values, the next one can take on d values, so if you have 2 random variables, you have d times d possible combinations. If you have n, you have d to the n possible combinations. Is that an issue? Yes, of course. Whenever you have something in the exponent that can grow, that's always problematic, right? That means we might need a lot of storage, might need to do a lot of computation to get things to work. When I said at the beginning of the lecture, we'll cover everything in this lecture, but then we'll see everything again in the next few lectures. This is what it's going to be about. Dealing with distributions over large sets of random variables. We're going to see how to do that in the next lectures, how to do that efficiently. For now, we'll just say, well, it's fine. We'll just work with it. It's exponential. We'll just work it out. And it'll be slow for now if we have a lot of random variables. Okay. Probabilistic models are anything that you might write down that defines a joint distribution. For now, the only way we know how to define a joint distribution is by actually writing down the joint distribution, but in the future we'll see different ways of defining joint distributions, more compact ways of defining them, and that will also be probabilistic models. Okay, so as a consequence, when we have a probabilistic model, what we have specified is random variables with domains. There are assignments, which we call the outcomes of the variables. We don't know yet what it's going to be, but then it ends up being something. The joint distribution tells us for every possible joint instantiation what the probability is. Has to sum to 1, so all these entries have to sum to 1. And what we'll look at in the future is a way of specifying these models where not all variables interact directly, so there are only indirect interactions between variables, and that will allow us to specify these models in a less kind of extensive way. You don't have to build a full table, but you can just specify interactions between small sets of variables. Just like in CSPs, where we're just able to specify constraints between small sets of variables, we'll see something similar here in the future lectures. Actually, a big parallel between CSPs and what we're covering in the next few lectures is that if we look at the two, joint distribution versus CSP, sometimes the main difference is that here you have true-false values saying whether it's allowed to have an instantiation or not, versus in probabilistic reasoning, we have a weight. How likely it is for this outcome to be the outcome that happens. Okay, then usually we want to abstract away from this big distribution and pay attention to particular outcomes that relate to subsets of the variables. So those are called events. So an event is some subset of all possible outcomes. So an event E is a set of possible joint instantiations. Could be, for example, all joint instantiations where the variable x1 equals true. So that's a set of joint instantiations. You can sum over all those entries compatible with that event. Let's say x1 equals true. And if you sum all the entries in the table, you get the probability of x1 equals true. The events don't have to be as simple as x1 equals true. It could be x1 equals true and x3 equals false, or yet more combinations of variables could be involved. All right, so let's do a couple of examples here. What's the probability that it's hot and sunny given this joint distribution over here? Okay, what do? We have to look in this table and find all the entries consistent with the event hot and sunny. Well, that means just this row over here, so that's 0.4. What's the probability that it's hot? Well, we check in this table, where do we have hot? Here and here. We sum those two entries together and we get 0.5. What's the probability that it's hot or sunny? Well, this is a more complicated event. Now it's okay to be hot or sunny. So any row where we circled something is okay. So we get 0.4 plus 0.1 plus 0.2, making together for 0.7. Usually, the events we'll care about are partial assignments, something about some subset of the variables, and we'll see a lot more about that later. So let's do a little quiz here. The quizzes today are kind of quicker quizzes. We're not going to do the normal format where you get to chat with your neighbor for 30 seconds. It's going to be the kind of quiz where we pop up a question, give you 5 seconds to think about it, and then we'll pop the answer into the slide. All right? So, first one. So we have a table over here, distribution over x and y. What's the probability for plus x plus y? 0.2. All right. What is the probability for plus x? How do we got the 0.5? Plus x is sitting over here. Sum these two together, 0.5. How about minus y or plus x? 0.6. How do we get that? There is a minus y here, a minus y here, plus x here, plus x here. Summing these three rows together gives us 0.6. All right, that went well. Moving on to marginal distributions. A marginal distribution corresponds to a subtable of the original joint distribution where you consider only a subset of the random variables. So let's start with a joint distribution and let's build a marginal distribution from this joint distribution. So we can build two marginal distributions here. We can build a marginal distribution just over T and a marginal distribution just over W. Okay, let's build the one over T. How do we get those numbers? Well, to get the entries here, what's sitting here is the probability for T being equal to hot, which means you look at the original table, see where it appeared, and then this part of this table is taken, you sum those numbers together, and that gives you the number over here. Same thing for cold. You can do the same thing for weather. So we can build similarly a table. Let's look at this one here. How do we get this entry here for rain equals 0.4? We looked at the consistent entries, which is here and summed 0.1, 0.3 together to get 0.4. So this new terminology, right? Marginal distribution means you marginalize the original distribution to be only considering a subset of the random variables, and you build a table for that subset of random variables. Okay, this is the general equation to build a marginal distribution, and it could be more than two random variables, of course. It could be 3, 4. If you had, let's say, a joint distribution over 3 random variables, then you could build marginals over just x1, a marginal over just x2, over just x3, or a marginal over x1 and x2, or a marginal over x2 and x3, or a marginal over x1 and x3. Okay, so let's do a quick quiz here again. Let's build marginal distributions. Let's build one for px. So what's the first entry here? And here is 0.5. How do we get that? We have plus x over here. Grab the consistent entries with plus x, sum them together, 0.5, minus x, we can do the same thing over here, 0.5. A quick sanity check is that these should sum to 1, right? This is a distribution. If you find these numbers correctly, it's guaranteed to sum to 1. If you're very confident, you skip the sanity check, and after you find the first one, you say, I know they're going to sum to 1, so I know what the second one is going to be. It's going to be 0.5 because they have to sum to 1. Everybody has their own kind of level of confidence in their first computation, which can determine whether they want to have the sanity check, then we'll just do the 1 minus the first entry. For y, probability for plus y, I'm here 0.6 because we have plus y here. Together that gives us 0.6. Let's be confident about this. That means the second entry is 1 minus 0.6, which is 0.4. All right, conditional probabilities. This is really the most important concept. Why is this the most important concept? Because that's what we're going to care about, right? We're going to care about if we measure something, what does that tell us about the things we don't get to measure? And that's where conditional probabilities come in. So what is a conditional probability? The conditional probability of having outcome small a for the random variable capital A, given random variable capital B took on value small b, is the probability of seeing A and B divided by the probability of seeing B. So let's illustrate this with this Venn diagram here. So the blue region is where we get the outcome A. The red region is where we get the outcome B. The intersection of those two regions is where we get A and B, and then what's left white is when you don't get A or B. What we're interested in here is the conditional of A given B. What that means is if we know the outcome fell in this space over here, that's all we know. The outcome fell in that region. What's the probability, given that we know the outcome fell in that region, that the outcome fell into the region where we have A? Which corresponds to then the probability of landing in this region over here, given that you landed in the bigger region in red. And so the definition, this is a definition here, is saying that we should take the ratio of those two, the probability associated with the joint instantiation A and B divided by the probability for the instantiation of just B. Think of it as frequencies, right? Let's say the area corresponds to the frequency you see B, the frequency you see A, the frequency you see both of them. Then when somebody tells you, hey, I know B is happening, you can, in this way, compute the probability that A is also happening. Okay, let's look at an example. Here is a joint distribution. It's now T and W rather than A and B, but it's the same story. What is the conditional for W equal S given T equals C? All right, well, we have a definition up there. The definition says that's equal to the probability of, and I'll use a shorthand notation because the domains are disjoint. Probability for S and C divided by the probability for C, which is equal to S and C we can read off right here, 0.2. C we cannot read off directly, it's a marginal probability, but we can read it off by summing some entries. So we have cold over here. We can sum these two entries here, giving us 0.5. And so we have a conditional probability of sunny given cold of 0.4. Okay, let's do a couple of quick quizzes on this particular concept. What's the probability for plus x given plus y? Now here are a few different things. The main thing I want you to do is I want to encourage you to think about this and think about what equation this involves and how this then plays out, right? So the equation involved is plus x, comma, plus y, divided by probability for plus y. The plus x plus y is 0.2. the plus y, there are two entries that have a plus y, it's 0.6 summed together, that's our conditional probability. How about minus x plus y? Minus x plus y, I'm hearing 2/3. This is 1/3, so you could say, well, x can only take on plus x or negative x. The probability for plus x given plus y is 1/3, so the probability for negative x given plus y has to be 2/3, right? This is equal to okay. So we had 2/3, no, we had 1/3 over here. We know this one is equal to 1 minus p plus x given plus y. And so we have 2/3. We could also compute it from scratch the way we did for the first one, but we'll just see that in action again down here. Minus y given plus x. And here 3/5. How would we get there? We have minus y comma plus x over probability for plus x. The first one is sitting over here, 0.3. And the second one plus x, we have two entries, sum them together, 0.5, and together we get 0.6. All right, we can do more. Rather than computing just individual conditional probabilities, we can compute complete conditional distributions. So we've seen one operation before. We've seen how to go from a joint distribution to a marginal distribution. We got a new table out, different table. Now we're going to go from a joint distribution to a conditional distribution. So a conditional distribution could look like this. Distribution for whether given temperature equal hot is a conditional distribution. We can compute each of these entries the way we've just done on the previous slides from this table over here. So this conditional distribution is a consequence of our joint distribution. We can do the same thing for temperature equals cold, and then together we get this family of conditionals, which we denote this way over here. So this might be a new piece of notation. This denotes a set of tables. Right? This thing here, the conditional of w given t, is a set of tables, one table for each value t can take on, and then for a fixed value of t, you get a conditional distribution table that looks like this, or for the other value, looks like this. Each of these individual tables sums to 1, because these are distributions. Happens to be a conditional distribution, still a distribution. Distributions sum to 1. Together, they happen to sum to 2, but that doesn't matter. They're really two separate conditional distributions here, paired together with this notation. All right. Now, one thing that is often used is something called the normalization trick. It's a way to go from joint distributions to conditional distributions in a slightly quicker way, also a little more mechanical. So might initially be a little less intuitive, but the idea is to go from a full joint to a conditional in a very structured way. So let's first take a look at what happens if we do what we've done so far. So we want to get a table here for the conditional for whether given temperature equals cold. Okay, that will have two entries. Here's the first entry we need to compute. We know how to do that, right? Use the definition of conditional probability, fill that in. Then we have to look up the consistent entries in the table. The bottom one doesn't have an entry in the table, but so let's write it out what we really need here from the table. Now we have an expression that has only terms that appear in the table. We can fill in the numbers and get our number that we wanted for the conditional probability of S given C. We can do the same thing here for R as follows. Once we've done that, we can fill in this table and we have our conditional distribution. That's just what we've done so far. Now, let's take a careful look at what's happening here. What entries are we using? We look at this equation over here, this equation over here. What's happening is that the entries we are using are all the entries consistent with T equals C. T equals C, 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 T equals C. So to go from this joint to the conditional, all we look at is the entries that are consistent with what we have here, T equals C. The way they show up is that all of them show up in the denominator. All entries in this table that have T equals C show up in the denominator. And then the one that shows up top is the one that has the variable instantiations consistent with the row we're computing. For the first row, it's sun, and then T equals C, and that's what we have on top, sun and T equals C. For the bottom one here, we have rain and T equals C, and that's what we have on top. And in both cases at the bottom, we just have all entries consistent with T equals C. So another way to look at this computation is to break it down and say we're really looking for all entries consistent with T equals C, and then we're going to use them in this particular way where we just need the one entry consistent with the conditional we're computing, but then we still need to divide by the sum of all of these entries. And that's the normalization trick. So this is how this plays out. The computation we just did, reorganized, you select all the entries consistent with the evidence, which was T equals cold. After doing that, you know that all you need to do is have the consistent one on top and the sum of all the others at the bottom. Okay, so what we now need to do is normalize. That's what it's called, this last step. We sum together all these entries, divide by the sum, and we get our conditional distribution. This just follows from what we did here, right? And here, we were just dividing by the sum of all these joint entries. This is very mechanical and can make it simpler to kind of go from a joint distribution to a conditional distribution. Question here.
When you guys say you give us the model, what does that entail? Just the joint distribution or all of these?
When we give a model, what that means is we give you enough to infer the joint distribution. For now, that would be a joint distribution. Later, we'll see that we might give you something else that allows you to, from that something else, find a joint distribution. If you can somehow recover the joint distribution, you have a full model for that set of random variables. If you cannot recover the joint distribution, you don't have a full model for that set of random variables. Let's do this normalization trick as a little quiz here, a quick quiz, work through it. So we want to compute the conditional for y equal minus y. That means we want to end up with a table here where for every value of x, we have some entries. So for x equals plus x, negative x. There's some probability here, which is the probability of that value for x given negative y. That's the table we're after. We know that the way we can get to this is just select the entries consistent with y equals negative y, which is this one and this one over here. So we end up with the distribution for x comma negative y. And x can take on plus x, negative x. And then the probability could be, in this case, transcribed, we have 0.3, 0.1. Now we know all we need to do is transfer these numbers over. The 0.3 will go there, the 0.1 will go there, but has to be, both of them have to be divided by their sum. The sum here is 0.4, so we end up with 0.3 over 0. Not enough space. 0.3 over 0.4 over here, and 0.1 over 0.4 over here. Where does this name come from, to normalize, right? If you think about what does it mean to normalize something, in a general context, you might say, well, to bring or restore to a normal condition, to make things normal. We'll use this a lot, normalization. Whenever we do probabilistic reasoning, it'll often come up that all that needs to happen at the end of the computation is to normalize. And for probability distributions, what that means is make things sum to 1. But that doesn't mean when we say normalize, we kind of arbitrarily make things sum to 1, right? If you have a 0.1 and a 0.3, which we had on the previous slide, you can make it sum to 1 by making the 0.3 and a 0.9 and keeping the 0.1. You can't just make it sum to 1 in any arbitrary way. When we talk about normalization, we talk about making it sum to 1 by multiplying by a constant factor. you find this constant, which on the previous slide here, that constant was 1 divided by 0.4. If you multiply with that, every single entry, you end up with something that sums to 1. So you compute this sum of all the entries, and then you divide every entry by that sum z. Here's the first example. We have a table, it's not normalized. How to normalize it? Well, z equals 0.5, divide each entry by 0.5, and this is what you get. Later, we'll also see that sometimes tables could look like this. The entries are too large. You can still normalize. It's just a mechanical procedure, right? You sum all of these entries together, which in this case sums to 50, and then you divide every entry by 50, end up with a normalized table. All right, let's take a short break here. And after the break, we'll start with looking at contest results and then wrap up our review of probability. All right, let's get restarted. Address for the occasion, contest results. All right, project 2 mini contest. Reminder, now you can be a ghost on your own side. You can eat the other players' Pac-Man when they try and eat the food pellets. If you do, then they sprawl all the pellets they were carrying and don't get to bring them back. All right. Fun names that are not in the top 10 because we'll see all of the top 10 later. It's baseline team. Just have a look. No time to do it. There will be midterms next week. And an unhappy face about that. Too School for Cool, who was one of our top contenders last time, became not very smart. I Raise Your ELO, MK, raised everybody's ELO rating, being the one ranked at the very bottom. Thank you from the entire set of participants. Top 10. At number 10, we have Test by Kevin Casey and Zayu Andrew Liu. They were the contest 1 winners, so we have a new winner this time. At 9, we have Test by Rohan Chitnis and Harrison Wang. At 8, we have OK Boat 2 by Aaron Zhou. The previous entry was OK Bot. Maybe the A was a typo, not sure. Only tested it once. What could go wrong? Alex Erpan and I forgot the first name, Jane. Then we have a staff bot, Staffy Duck, sitting right there, but we don't count them in how we count top 10. So no number assigned to staff, but right there. At 6, Wisalama by Sean Hickey. Wislama. At 5, we have Roger Shen with 1500. At 4, we have Girl, Look at That Body. That's a good one. Maybe Kenwa-san can report back after the weekend how this worked out. Top 3. In ASCII order. I had to look this up because you guys were not all starting with letters, and I wanted to have some, way of presenting them without already giving away who might be first, second, or third. 89 Temples, Joseph Hui and Alan Yao. Is any one of those two here? Over there. So in the top 3, 4th place in contest 1. Even ourselves cannot understand our bots make those moves. Fan Ye and Tianhao Jiang, 2nd place in contest 1. Is Fan Ye here or Tianhao here? Over there. All right. And then, is this a cat face? I don't know.
Smiley face.
Smiley face.
I was going to make it different.
Very horizontal smiley face. Alex Sawai right here, and Zahin Aziz. Is Zahin here? Over there. All right. So we have over there, over there, over there. Make your pick. They stood 24th place in contest 1. All right. Let's see how this played out. We'll do it like last time. Of course, it plays out based on the ELO ranking, but I'll pick 2 of them. One of them is going to be third. The loser of the game you're going to watch is going to be third. So we'll look at smiley face versus 89 temples. Strategy underneath. For smiley face, determine whether to play defense or offense, divide food amongst offensive agents, evaluate when to go home, evaluate when to switch from defense to offense or vice versa. During match, reassign target food groups, prune the search tree to allow for deeper search, evaluate danger levels. All right. 89 temples, standard alpha beta search, iterative deepening, prunes branches that look like trashing, defender's heuristic tries to block all exits, and then some secret sauce that's hidden because the next contest might be quite similar, in fact, to this contest, and they want to keep their advantage. All right, let's look at this match. We have smiley face against 89 temples. Smiley face in red, 89 temples in blue.
That's like basically all of them. Like, I'm going to say that's 80% of matches.
It's kind of a deadlock. But the score is at 1 for red, so red is ahead. You only need to win by 1, and your bot managed to take advantage of that and just lock it down with a 1-point advantage. All right, so in third place, we have 89 temples. Congratulations. For second versus first place, smiley face, which we already looked at, and even ourselves cannot understand the moves of our bots, I think is what followed. Using some heuristic to find and prioritize entries to the maze. Agents guard the 2 most valuable entries. Only steal foods when it's absolutely safe. Pac-Man cannot be eaten. Okay, let's take a look at that. Smiley face in red. Even ourselves cannot understand the intelligence behind here. In blue. Let's see what happens this time. The blue Pac-Man has been kind of locked down for a while there. A little bit of waiting, but it's ahead. Red won this one. Congratulations to Smiley Face. I will say though that it was not easy to pick the games because it turns out, I will say the Smiley Face, which came in first, did really well against all the other bots, but against the top 2 bots, it was kind of a break even, if not a little bit in favor of the number 2 and number 3 if those were just the 3 bots. But then based on how well it did against all the other bots, it had a higher ELO ranking than the ones who came in 2 and 3.
Also, do you guys take food, like the win into consideration?
Not in the ranking. The amount of win doesn't matter, just win or lose or tie is what counts for the ranking. So we watched that one. Let's see, is that twice the same thing here? That is twice the same thing. Here's the total top 6, including the staff bots. So you also managed to be ahead of the staff bot, which is always good. The staff bot is based on the one that won last semester, so it's always a good thing to beat the previous semester winner. Just want to congratulate the entire top 3 here. Congratulations. Of course, everybody who participated is a winner in this contest, so. You can be one of those winners, no matter how well you do next time. What will Project 3 mini contest be like? What's different between 2 and 3? Well, one thing to keep in mind is the winner of contest 2 stood 24th on contest 1. So don't be feeling like, oh, didn't do so well yet, I don't stand a chance. No, you can still jump in after the midterm, is what I recommend, and work in the Project 3 mini contest. What's going to be different is that there's a stub of code, so the rules of the game are the same, but there will be a stub of code. That stub of code will allow you to write a file. As you're playing the game, you can write to a file, think at the end, and you can read that back at the beginning of the next game. So you can do learning. So you can write out, let's say, a set of weights that you played with, and then if it was better than the previous set of weights, you can write out that it was better, and next time you can then use better weights. You can do learning on the contest server if you want. Yes, Patrick?
Do you have the identification of what you're playing against? So can you tell which agent you're playing against?
I don't think you can tell which agent you're playing against.
It's developed a general strategy rather than one.
Yes. Question?
You play more than one time against each.
Well, you can play as many times as you like, because you can request games, right? So you could request games against a particular bot 10 or 20 in a row, see what happens, right?
But I mean, like in the rankings, does it like test your training algorithm by running it like 10 times or something, and then?
Well, that's a good point. You'll have to decide. You could use this training effectively ahead of the final decision, right? You could use the training, and then maybe you could say, I'm not doing training during the actual competition, because who knows what's going to happen if I play bad bots and I then tune to a bad bot and then I play a good bot and all of a sudden I start losing. So that's up to you. It will, whatever code you have, if it's code that trains, that training will be in effect during the thousands of games that we played to finalize the ranking.
Oh, so the file persistent.
Yes. But when you resubmit, you can overwrite it. Well, your code, you submit a .py file, but the code in that file can overwrite the file that's stored on the server.
Since this one we can learn from playing people, is it possible to speed up the test server a little?
That's a good question. Yeah, we'll look into that. I think it's possible. Okay, so we just looked at normalization. What is in general probabilistic inference? What is this thing that we're going to be doing for the next few lectures? It's computing some desired set of typically conditional probabilities from some initial set of probabilities. The kind of default scenario would be you're given a joint distribution and you're asked to compute something from that. The reason this is interesting is because often as you get more evidence, you get to measure more variables, your distribution will change. For example, it could be that the probability for getting to lecture on time, I didn't come late on purpose today, but it kind of fits well with this example here. The probability of getting here on time could relate to having no reported accidents, and could be maybe 90% chance on time giving no reported accidents. But then if you in addition know that it's 5 a.m., probability of getting someplace on time is even higher because it tends to be quieter at 5 a.m. on the road. And then if in addition you now also know it's raining, it can drop again, because you know that in rainy traffic things go slower and so forth. And that's really what we're going to be after, is this kind of how the distribution or the conditional distribution changes as a function of the amount of evidence we have. Here's the first procedure, a very canonical procedure that we'll be using now, and it'll come back in future lectures, which is inference by enumeration. The idea here is when you're given a query, and in this case the query would be of the type, what's the probability for a set of variables, Q could be more than one variable, Q given some evidence, and again, E, capital E here could be multiple variables. What is this conditional distribution? If we look at that query, we can split our set of variables in our full joint distribution into 3 groups, disjoint groups. The first set of variables is the evidence variables. Those are the ones we have observed. We know what the value is. The second set is the query variables. Those are the variables we want to know something about. The third set are the hidden variables. Those are variables that appear in the joint distribution, but don't appear over here. Why are the hidden variables there? Because you started with a joint distribution that had a lot of variables in it, and the query was only concerned with a subset of those variables. All right, so this is what it could look like. Here's a generic procedure to get out the answer to the query. Step 1, select the entries consistent with the evidence. So you would look at your evidence, and in the joint distribution, look at that table. Every entry in the table that's consistent with E1 through EK. So it has to be consistent with all of the evidence variables, not just 1 or 2 of them. All of them have to be consistent with the evidence, and then you grab that row and keep the rows that are consistent. Then the next thing you do, and this metaphor will come back later, just kind of squeezing things out, is we'll sum out the hidden variables. What that means is we're left with a table here with only the rows that are consistent with the evidence, but that table still has both query variables and hidden variables. We now want to get rid of the hidden variables. That's what we do next, sum over the hidden variables, and this is the equation you use. And we'll see an example on the next slide. But this is a general equation that you use to do this. What is this saying? It's saying that the probability for Q and the evidence is equal to the probability for Q and all hidden variables and the evidence, and then we need to sum over all possible instantiations of the hidden variables. All right. This is an example. In the simplest form, this would be something like P, A, comma, C equals sum over B, P, A, B, C. It's the same kind of equation. Naming it the way we name things here would be something like P, Q, comma, evidence equals sum over H, P, Q, H, E. In general, of course, this Q and E can be more than one variable, H can be more than one variable. And that's what's shown at the bottom here. Once you have done that, you have the joint between Q, which is still a variable. It's a capitalized Q, so it's still a variable. We still have a table here. This is a table with as many entries as values Q can take on. That table is not the conditional yet. It's a joint between Q and that particular set of evidence. All we need to do now is to normalize, and we get out the conditional distribution. Why is it that all we need to do is to normalize? Well, we have this joint here. We know that to get the conditional, we need to divide by the probability of the evidence. The way to get the probability of the evidence from this quantity over here is to sum over all instantiations of Q. Because that way we get the probability of the evidence. And that's what Z is the sum over all instantiations of Q, gives us the probability of the evidence, we divide by that, and now we have a normalized table that is the conditional distribution for Q given the evidence. All right, let's look at these mechanics in action on this slide over here. How about PW? This case, what's our query variables? Query variables, W. Evidence variables is the empty set. And hidden variables is, in this case, S and T. All right? So what this is saying is we grab everything consistent with the evidence. The evidence is empty. So that means we grab everything, because everything is consistent. So we have the entire table after the first step. Next step is to sum out over the hidden variables. All right? Sum out over the hidden variables, what does that mean? That means that we're going to end up with a table that is, in this case, PW. We'll have an entry for sun and rain, and the values of those entries will correspond to summing out all consistent entries. So here we have sun, 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 sun. That's consistent with S here. Sum those together, we get 0.15 plus 0.1, 0.25, 0.35, 0.65 over here. And then we take For rain, we have these entries over here, sum them all together, and we end up with 0.35. So that was inference by enumeration in action for this particular query. How about the next one here? W given winter. So the query variable is still W. Evidence variables is now the season, and the hidden variables is, in this case, temperature. First thing, pick all the rows in the table consistent with the evidence variables. Get rid of everything else. So evidence variable winter, so we get rid of all of this up here. Just keep the rows consistent with winter. Next step is, after we've done this, we have a table here, right? If we look at this subtable here, hold on, this table here, it's a distribution for the query variables, which is W, the hidden variables T, jointly with the instantiation of the evidence variable, which is small w. Not ideal. Let's maybe just write it out as winter. That's the table we have right now. Next step is sum out over the hidden variable, which is T. What does that mean? We're going to end up with a table for W, comma, winter, and W can take on the values sunny or rainy. The probabilities we'll find by summing together. For sun, we look over here, sun and sun, sum these two together. That gives us the entry here. The other entry is the other two values, also 0.25. At this point, we need to renormalize to get the conditional distribution. So we divide by the sum of these, which is 0.5, and we get the conditional distribution. So now we divide by the sum, which is 0.5, and that makes it into the conditional distribution. All right, let's do the last example here. So query variable is W. Evidence variables is, we have winter and hot, so the other two variables are used there. And then hidden variables is empty. Pick the rows consistent with the evidence, winter and hot, which is over here. That gives us the following table for weather, comma, winter, comma, hot, which is shown over here. Next step is to sum out over the hidden variables. There are no hidden variables, so that's a no-op. We don't have to do anything. Next step is to normalize to get the conditional distribution. So now we normalize. The sum of these is 0.15, so we divide by 0.15 and 0.15, and that gives us the conditional distribution for, wait, did we do something wrong here? Yes, no, we did it right. Gives a conditional distribution for sun and rain, so the weather variable given winter and hot. In this case, we end up with sun, rain, 2/3, 1/3 probability, and this is the conditional over here. All right, let's stop here and continue with the last parts of probability in next lecture.